Yeah.
Yes. Yep.
Yeah.
Okay, so first thing you need to do is you guys need to learn about phase changes. So we did specific heat already. So specific heat was when you took an object and you wanted to increase or decrease the heat by 1 degree, right? So everything has a different specific heat. A lot of them are listed on your reference table, so on and so forth. So while you guys are thinking about specific heat. So specific heat is only going to happen during a single phase. So you're only going to have specific heat changing during either a solid, a liquid, or a gas phase only. Okay? Which means that our potential energy is not changing, right? Because if we're in a single phase, that means that we are in the solid, the liquid, the gas phase, which means our temperature is changing, which means our kinetic energy is changing. Yes? You guys get that?
Yes.
Okay, cool. So, all right. Well, what happens when we have a potential energy change? Well, potential energy changes are only going to happen during phase changes. So that's going to be melting, freezing, boiling, vaporization, condensation, sublimation, so on and so forth. Well, how do they change? Well, it's the same way that if a substance is increasing in kinetic energy, then their potential energy will also increase during the next phase change. So if you're adding in heat, right, even though the kinetic energy is not changing during the melting and the freezing point, okay, it will end up having the potential energy change. So for example, like I said, if you have the melting phase, right, and you also guys are responsible for knowing that melting is when you go from a solid to a liquid, okay, you're going to increase your potential energy. All right. Melting is also known as fusion. It's a different one than nuclear fusion. That's why you have to specifically say, when you're talking about this, we're talking about fusion. Okay. Then you have solidification or crystallization or freezing. Okay. And your potential energy is going to decrease in that point. Okay. Because you're releasing that energy. Notice how I didn't say you're releasing that heat, because during a phase change, your temperature does not change, right? Then you have vaporization. Okay, vaporization is when you go from a liquid to a gas. So your potential energy is also going to increase, because if you're a liquid and you want to get hotter and become a gas, you're adding energy. You're adding energy. Then you have condensation, and condensation is when you decrease your potential energy. Condensation is when you go from a gas to a liquid. Okay, the next two you may or may not know. Okay, they are sublimation and deposition. Sublimation is when you go straight from the solid phase to the gas phase. So something like dry ice, right? It's considered dry ice because it never gets wet. It never goes into the liquid phase. So dry ice, a lot of times you will use when you want to create a smoky effect. So like during Halloween, if you want to have a cauldron set up wherever your, fruit punch is, and you put it in, but you want to make it look like it's smoking over, you use dry ice that way. You also use dry ice by when you send food from one location to another, like one state to another. So if you order something online and it's something that needs to be refrigerated or kept cold, they do it with dry ice. Okay. You guys okay? Can I move on?
Yeah.
Okay.
Wait, Miss Gonzalez?
Yes.
What does PE change only mean at the top?
Potential energy.
Okay, and what does like the increase and decrease mean in the parentheses?
If we're increasing in potential energy or decreasing in potential energy.
All right, thank you.
No problem. Okay, so I want you to draw 3 boxes in your notes that look like this. Okay. And I'm going to join you here. Come on. Okay, so you should have at this point 3 triangle boxes basically. And what we're going to do is we are going to be drawing what's known as particle diagrams. Hi. Raj is looking at me funny. I'm just making it look nice. Okay, so if we have, all right, a solid, you know what, this is not working out. Okay. Okay, we have a solid, a liquid, and a gas. All right, what are they going to look like? Well, inside of the substance, right, you are going to have particles. Well, those particles are going to each look differently.
Miss Gonzalez, do you want us to draw this in the little boxes that we drew? Okay.
Yep. Okay, so you always need a key, guys. When you are doing this, this is going to be a monatomic substance. This is going to be something that is by itself. So something like helium, right? Helium or neon or Raja. Okay. So in the solid form, you have the molecules that are super close together and they're going to be vibrating. In a liquid form, they're going to be a little bit further apart, okay? And they're going to be moving, right? And in the gas phase, they're going to fill the container completely and be out of control. If you were to do this as a diatomic, okay, just so that you guys can see the difference, okay, this is a diatomic, okay? This would be something like, okay, hydrogen. Because hydrogen in its natural state is bonded to itself. Okay, that's what's known as a diatomic. So at room temperature, at SDP, at basically its natural state, it's bonded to itself because otherwise it's so reactive. Hey. The joys of working from home. Okay, so I want to show you really quickly what that's going to look like. She's throwing her toy around. Okay, let's see. Yeah, I was trying to get our COVID vaccines. See, does it come on? If you guys want to follow along and do this yourself, you can. Okay, we have these things called PhET simulations, which basically takes anything that you're looking at and it will help you to actually see it happening. So where is the phase change one? I had it up, it disappeared. This one? Do that one or the one next to it? Okay. We're just going to do this and make my life easier here. Okay, so if we're going to look, these are all monatomics, right? So in the solid phase, you can see that they're still moving. You can see that they are really tightly together. They're neat, they're organized, right? In the liquid phase, they're a little bit further apart. They're moving more, but they do not fill the container. But in the gas phase, they're all over the place, okay? They're throwing themselves around. They are in the most excited part is the best way to explain it, okay? And they're all over the place. So that's a monatomic. Argon's the same way. Now, if you wanted to look at a diatomic like hydrogen or oxygen, right? You see how they are still tightly packed in the solid phase, but they are bonded to themselves. They're both the same color. They're both the same shape. They're both colored in, okay? So liquid, same thing. Kind of looks like ants on a hill to me. And then gas is just all over the place, okay? Now, water, however, water kind of looks like Mickey Mouse, right? In the gas phase, water is all over the place, like normal, right? It's spinning, it's moving, it's doing everything, all right? In the liquid phase, it's still the typical, what you would expect from a state. However, in the solid phase, they're not tightly packed together. They have these extra spaces in between, which lets air in between. So as it solidifies, it ends up looking like this. This is why water is less dense in the solid phase than it is in the liquid phase, and ice is going to float because it has those air pockets or spaces in between. Okay, just a fun little fact here. Okay, now, I'm going to steal again. We're going to do what's known as a phase change diagram. Okay? A phase change diagram, right? We did the particle diagram, so on and so forth. A phase change diagram looks like this. I love when things just delete itself. Okay, so I want you to draw this into your notes. I'll give you guys a second to do that.
Wait, Miss Gonzalez,
What's up?
I'm kind of confused, like, about, like, what exactly a diatonic, like, diagram is.
Like what is?
Yeah.
No, I can't hear what you said.
Like, I'm kind of confused about, like, the different diagrams.
Between a solid, a liquid, and a gas?
No, the diatonic, like you were saying.
So a diatomic just means it's the same thing bonded to itself. So it would be a hydrogen atom and a hydrogen atom bonded to itself at room temperature, at STP, in its natural form. Hydrogen, oxygen, there's 11 of them that actually will bond. Oh, not 11. They're called Brinkelhoffs, but you don't need to know that for this class. But you'll just need to know that they do bond to themselves.
So, but Ms. Gonzalez, what is this? What is this specific diagram, the phase change diagram? Like, what does it have to do with everything else?
Well, you haven't gotten that far yet, right? We've been talking about energy, right? So I'm about to tell you about it. So here are all the diatomic elements. They're called Brinkelhoffs. It's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Marcia, stop! She has her bone and she's throwing it around. I'm sorry. Okay, so we have been talking about energy, right? So a phase change diagram, I'm going to put everything that we've learned together into one nice, neat picture. Okay, so the first thing you have to do is label whether there are phases or there are phase changes. Anytime that you see that angled line, that's where a phase is going to be, and that's where you're going to get the change in kinetic energy, right? Because that is where we're having temperature changes. Okay, so this is where you're going to have a solid, because it's at the lowest temperature. This is where you're going to have a liquid. And this is where you're going to have a gas in its single phase, right? We're not changing phases at that point. At this point, it is just the phase by itself. How do I know? Because we're increasing the temperature. If you're increasing the temperature, that means you are changing the kinetic energy. Okay, the two plateaus or the two flat lines are going to be where you are going through a phase change, right? And the phase change, you can just write one of them. You don't have to write all of them. When you go from a solid to a liquid, is known as melting, right? And this is where you're going to get your change in potential energy. Right? Up here is where you're going to get your vaporization, and that's where you go from a liquid to a gas, right? And that's where you're going to get your change in potential energy. I know you want attention.
Wait, what does the first one say? Melting is, oh,
Now to a liquid. Now, for those of you who are planning on going to chemistry next year, you're going to want to save this when it's completely filled out and take it with you, because everything I'm going to teach you today will be in one of the first units you do in chemistry. Okay? I'm giving you a little bit extra information that you need to know. You don't need to know all of it for earth science, but I'm not going to tell you which one you need to know for chem versus earth science, because you're going to learn both of them for this class.
Miss Gonzalez?
Yes.
You wrote something on the top of the graph. I didn't understand what that was.
Where the diatomics are?
Yeah.
This?
Yes.
So Brinkelhoff stands for the elements themselves. So this is going to be bromine. Oh my God, I have the worst handwriting on this thing. Right, this is iodine. This is nitrogen. This is chlorine. Hydrogen. Oxygen. And fluorine. Okay, those are all of the elements that will show up as diatomic elements in nature. The ones that have the same thing bonded to itself. Everything else on the periodic table will be monatomic or just by itself. So when we were looking at the states of matter little FET that I was showing you, okay, neon and argon were monatomic, or it was one sphere by itself, right? But when I clicked on oxygen, right, it was the two orange spheres together, right? Because it's an oxygen molecule with an oxygen, or an oxygen atom with an oxygen atom. Okay, that's just something off to the side.
Okay, thank you.
No problem. So let's go back to the phase change diagram. I'll leave it up for you to see a little bit. Okay, the phase change diagram. So now we know where there's going to be a change in potential energy and a change in kinetic energy. So where there's a change in kinetic energy, you would use that MCAT formula, the M D delta T, right? Because you're changing the temperature. So that's where your specific heat would come into play. All right? So some of you would say, oh my God, stop. Okay, you can't have it. No, you can't have it. You can't. Stop. Okay? So some of you would say, well, if there's an MCAT formula, is there a formula that you would use during melting and freezing? And the answer to that is yes, there is. There is definitely a formula that you would use during melting and freezing and vaporization and condensation. And so the first formula would be MHF. Remember I said melting is kind of like fusion, right? So that's melting, mass times fusion, right? And then this is going to be MHV. Where HF is heat of fusion and HV is the heat of vaporization. Okay, now why is this important? I will show you in a second when everybody has this copied down. Let me know when you guys are ready. You have time. Don't worry. You guys good?
Not yet.
Okay, take your time. I'm going to go kill my dog. I'll be right back. Stop throwing this around. Come here. Come here. Sit here. Sit here. Sit here. Chew your bone. She's still alive. Don't worry. Okay, so the MHF and the MHV formulas. Notice what is not there. There is no specific heat there. Okay, there's no capital C. Since there's no capital C, it means that there's no specific heat, which means there's no change in temperature. Okay, so during melting, vaporization, freezing, condensation, there is no change in temperature. Okay, that's why you don't use the specific heat capacity, because there's no change in temperature at that point. Okay, so I want you guys to go to your reference tables on page 1. Okay. Right? Now, if you look in the top right-hand corner, it says specific heat, right? But then right underneath it, it says properties of water. Okay? Now, this is your HF and this is your HV values for water. Just like for specific heat, each individual thing has a different specific heat. Each individual thing has a different heat of fusion and heat of vaporization. Okay, so when you're looking at this, right, If it says melting or freezing, you're just going to use HF. And if you notice, HF is very small compared to HV. This is specifically for water. What this tells me is it takes 334 joules per gram. So it takes 334 joules for every 1 gram of the substance to melt one particle, basically, or to melt 1 gram. Right? So you have to put in 334 joules per gram in order to do that. Okay? During that time, okay, during that phase change, when you're going from a solid to a liquid, you are going to have both the solid and the liquid phase. Okay? So if you look here, right, this is exactly what I was saying, right? We have the solid phase, and then we have both the solid and the liquid, then we have the liquid phase, then we have both the liquid and the gas, and then just the gas phase. So as you're going through this, you're solid, 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 solid. Then the second it plateaus out, you get a solid, liquid, solid, liquid, solid, liquid, solid, liquid, till all of those solid becomes a liquid. Then you start to increase in temperature again. So right here, right where this dotted line is, okay, is where you're going to start getting your liquid only phase. And then when it starts to go through a phase change, you have both phases happening until again it starts to increase in temperature. Right? Then you're only in one phase. So anytime you have a plateau, you have 2 phases at the same time. Okay? Anytime that you have a increasing or a decreasing, increase or a decreasing slanted line, depending on if we're increasing or if we're decreasing the temperature, that's when you're going to have a phase only. Why is that important? Because that's where you're going to have your kinetic energy changing. And your potential energy is only going to change when you have those plateaus. Okay? So when you're looking at this, like I said, right, you are going to have, in order to do this, you need to have, okay, for water, 334 joules per grams for you to go from a solid to a liquid, or you need to decrease by 334 joules per grams in order to go from a liquid to a solid, because of the fact that you have to release it. So it's the same thing with specific heat, where you have to increase it or decrease it. So in order to melt water to go from a solid to a liquid, you have to increase the energy by 334 joules per gram. In order for you to go from a liquid to a solid, you have to release 334 joules for every 1 gram of water. Okay? Now, if you look, I said there's an HF and then there's an HV, V for vaporization. Well, here you go. Right? We have it down here on the second part. We have heat energy gained during vaporization and heat energy released during condensation. Right? So heat energy gained during vaporization is 2,260 joules per gram. Now, that is a ton of energy. And if you look, I did it on purpose. In our phase change diagram, right, the line for vaporization, the plateau line for vaporization, is longer than the plateau line for melting. See, look. Okay, you see how the vaporization line is longer? Do you see how the liquid line is longer? And the reason for it is because you have to put in more energy in order to overcome what's known as intermolecular forces of attraction. Okay? Intermolecular forces of attraction. Okay, that's the reason why things stay as a solid, right? The reason they stay so close together in a solid, yes, there's less kinetic energy, but at the same time, there's a little bit of an attraction from one atom to the other, okay? That doesn't mean they're doing anything. That doesn't mean they're bonding with each other. They're just there. Those intermolecular forces of attraction, okay? It's how molecules interact with each other, all right? To overcome those intermolecular forces of attraction, right, for between a solid to get to a liquid, you don't need that much energy. But in order to go from a liquid to a gas, you need a ton of energy. And if you think about it, it should make sense. Why? Because if you look at the difference during the phase change diagram, right, and also the little FET we have here, right, when you go from a solid to a liquid, not much has changed, right? A solid is rigid and fixed and together, whereas a liquid is a little bit further apart, right? But they're still pretty close to each other. They're still really attracted to each other, right? The difference between a liquid and a gas is completely different. A gas goes all over the container as long as it's closed, right? They're moving all over the place. They kind of have minds of their own. Look at the difference, right, between that and a liquid. A liquid is still kind of together. They're still kind of put together. So you need a ton of energy to go from a liquid to a gas or a gas to a liquid, okay? That's why when you were looking at the reference table, right, it says that you need 2,260 joules of energy for every 1 gram of water to go from a liquid to a gas or a gas to a liquid, because you have to overcome that attraction in order to do this. All right, does anybody have any questions?